Hello, in this video we're going to take a look at gas pressure and we're going to take a step into the microscopic here. We've moved into looking at ideal gases, so we've made all these assumptions to make things easier in order to analyze a gas as an ideal gas. So now we can look at these individual particles in the gas and try and get a microscopic underpinning to all these macroscopic gas laws that we've been looking at previously. So, things like Boyle's law and all the other relationships between pressure, temperature, and volume. Right, so let's start then with what gas pressure is. Well, we know that pressure is a force divided by an area. So gas pressure is going to be the force per unit area exerted by a gas onto any surface that it comes into contact with. So if we've got gas in a box, then we're going to have a certain force exerted on the box by the gas. Divide that by the area, surface area of the box, we've got our pressure. Now, where does this force come from? This is going back to our classical mechanics now. We're going to look at Newton's laws. So for Newton's second law, if we got a wall of the container and we've got some molecule in the gas or atom in the gas, whatever it might be, it comes over, it hits the wall of the container, it then rebounds. Of course, we're assuming this is an elastic collision. It's one of our assumptions in our definition of an ideal gas. So we're getting here a change in momentum, which means that we're going to get a force from Newton's second law. So this is driven by Newton's second law. Again, we've got the assumption in our ideal gas that, okay, the gas might be moving around quickly. We might have fast moving atoms and molecules in the gas, but they're not relativistic. We can still analyze them and describe them using Newton's laws. So that's all fine. I mean, clearly from this description, we're going to get an increase in pressure if a whole load of different things. I mean, we could have more particles. So say we had more particles in the gas, that means we're going to get more collisions. So we're going to get greater force. So we're going to get greater pressure. If the speed of the particles is increased, and that means then that we're going to have a higher temperature. So if the temperature has gone up, we're going to have a greater pressure. This is one of our gas laws, that we're going to have pressure being proportional to temperature for a fixed mass of gas. So we're not changing this bit around, we're not changing the number of particles, and for a constant volume. So we've got that happening. If we decrease the volume, we're going to get greater pressure because we're going to be having more contact with the, more collisions with the walls of the box. So if we've got more collisions, then we've got a greater force. So that's another thing that we could have, is if the volume goes down. So that's giving us our pressure is inversely proportional to the volume. You put the temperature up, you're getting more collisions and you're getting a greater change of momentum with each collision. So that's why we're getting that one. Put the volume down, you're getting, okay, it's the same change in momentum with each collision, but you're getting more collisions because they're going to be hitting the walls more often. So you can immediately see where the macroscopic gas laws are coming from by analysing the gas at the microscopic level using Newton's second law. Now we can go further than this and get a new derivation of pressure by continuing this microscopic analysis. Now the usual way this is done is they'll take a cube with side L, and inside that cube they'll put a single gas particle and they'll have it moving from side to side. So if we've got our 3 dimensions of the cube, the motion of the particle is just in the x direction. So we can say it's moving with some speed c subscript x, and we want to look at the collisions that it makes with one particular surface of the box. So we're going to then say, okay, well, the force is going to be the rate of change of momentum. This is our Newton's second law. So if it's got a mass of m, then it's going to come onto the wall with mcx as the momentum, and it's going to go off of the wall with minus mcx. So we're getting a change in momentum of 2 mcx, and how often is it going to be hitting the wall? What is the time between collisions? Well, after it's hit the wall, it's got to travel distance L over at the opposite face. Then it's got to come distance L back again. So it's doing a distance of 2L divided by cx in order to get the time. That's the velocity or the speed that it's moving at. So that is going to give us the force from one particle when it's colliding with that wall, which gives us what, mcx squared over L. Now this is where Newton's third law comes in, because looking at the change in motion here of a gas particle, really we've said there the force on the gas particle from the wall. Well, by Newton's third law, we're going to have exactly the same magnitude force in the opposite direction, going outwards on the wall from the gas particle. So we need to say something then about Newton's third law, about how we're getting that relationship between the change of motion of the gas particle, which is really what we're working out here, and how you're getting the same then force on the outside of the box. So we need to now generalize this, because of course this is just telling us an impact on one face by one particle. So we need to start stepping this up to say, well, now we've got n particles, capital N particles. We haven't just got one of them, we've got capital N particle, and that they're moving in all directions. But because they're moving randomly, we can say that cx squared plus cy squared plus cz squared is not only equal to c squared, the total speed that we've got of a particular particle, but we can also say that they're all equal to each other. So cx squared is going to be equal to, once we've averaged it all, this is the key thing, we want to average them all, and that's the symbol we're putting a bar over it, is to say we've averaged these things. Then that is going to be a third of the average of the total velocity, because there's nothing to distinguish between cx, cy and cz. They're all the same because things are moving at random. So once we've averaged it up to n particles, they're all going to be the same as each other. That's the random result of it all. We can also say that the force from a random particle is going to be putting a bar on that as well, because that's what we're interested in. When we step it up to n particles, they've all got a different component of their motion in the x direction. So we want to average that out. We want to get the average force. That's what we're looking at here. If we're going for the average force, well, nothing changes with the mass. We say in an ideal gas, they've all got the same mass. These particles are indistinguishable. L is the length of the box regardless, so that doesn't change. The only thing we're averaging to get the average force is that component of the motion in the x direction. So that's what we're averaging. We can now put all of this together and say, okay, what's our total force then for n particles? Well, we have to have n lots of it. We certainly have to multiply by n. We know that we're getting a mcx squared with a bar on over L. So we know we've got that, but we also know that our cx squared with a bar over, our average square of the x component, is a third of the average square of the velocity. So we've now got 1/3 n m c squared with a bar on. So that's what we've got for our total force. Now we want to get, I've left the L off, divided by L. Now we want to get our pressure, which is the force over the area, and the area of L is L squared. So our pressure, which is F total divided by L squared, well, we can now see what's going to happen, because we're going to have an L cubed on the bottom, which is the volume. So we've got 1/3 nm c squared, average square of the velocity, and then divided by the volume. So this is now giving us our new formula that we can work out. It's giving us the pressure, or we're getting that PV equals 1/3 nm c squared. So that's a new microscopic, derivation, a new microscopic formula for how we can quantify exactly what's going on with pressure and volume according to the number of particles we got in the gas, the mass of each particle, and then the average of the square of the speeds of those particles. So this gives us our second relationship now, where we've got a PV on the left-hand side of a formula. Yeah, we saw this before with our ideal gas laws, where we had PV over T as a constant. So we've now got two things that we can start linking together. We've got another connection here between the macroscopic, which is what we were looking at here, and the microscopic, with what we're looking at here. And that's what we're going to start exploring in the next video, and we start getting into the realms of the Boltzmann constant. And yeah, that link, we finally got a link between the macroscopic and the microscopic. So let's explore that a little bit further, but I'm going to put that in a separate video because I've gone on quite a bit in this one already.